Kia ora. Differentiation of composite functions. One of the rules of differentiation we learn at level 3 is the chain rule. It helps us deal with more complex functions. We use a substitution type method with the chain rule. So what does the chain rule look like? You can actually find this on your formula sheet. The first statement there is saying that you may have some function y, and within that function is actually sitting another function called u of x. The second way of describing it is dy over dx equals dy over du times by du over dx. And what you can see has happened there is if you were actually going to cancel out the du's, you'd end up with dy over dx. So it's kind of just breaking it down, and that's into two functions, or the two composites are coming together to make the one function. So that's where that name comes from. So let's look at some examples of the chain rule. Example 1. Differentiate the function y equals 2x squared plus 3, all cubed. So if you look at that function, what's happening to x itself is it's like it's gone through a machine and been squared, multiplied by 2, and 3's been added on. Then it's as if it's gone to a second machine where it's then been cubed. So if we just focus on the inner part of what's happened first, let's call that u. So we'll say let u equal 2x squared plus 3. According to the chain rule, we need to work out what du over dx is. So why don't we differentiate that now? If we do that, then we're going to get 4x. If we then focus on that second function that's occurred, then what's happened is in that process, that outer process, it was cubed. So looking at that, we can say that y is equal to u cubed. If we then look to differentiate dy with respect to u, and get dy over du, then what we'll get is 3u squared. If we then write down the chain rule, dy over dx equals dy over du times du over dx, we've actually all got the bits of information we need. So we just substitute those in, and we're going to have 3u squared times 4x. But wait on, we know that u is 2x squared plus 3, so we just write that in again, and then we just simplify where we can. So we can just go 3 times 4x is 12x, and we can just leave it in that format there. We don't need to expand it. Example 2. Differentiate y equals 3 over x squared plus 1. So if in this case we look and say the first thing that happened is we had x and we squared it and added 1, that would be the first part. So let's call that u. So u equals x squared plus 1. If we differentiate that to get du over dx, that would give us 2x. If we now look and just focus on the second thing that occurred there, that's going to be the 3 divided by that bottom line. So we could say let y equal 3 over u, which is the same as 3u to the power of negative 1. Then if we differentiate that, just multiplying down negative 1 times 3, so we've got negative 3u to the power of negative 2. We can rewrite that as negative 3 over u squared. Then we can use the chain rule and just substitute in those pieces that we just worked out. So that means we're going to end up getting dy over dx is negative 3 over u squared times 2x. But we can substitute in, once we simplify down, to negative 6x over u squared. We can substitute in that u, so we end up with dy over dx, which is the gradient function or the derivative. They're just all different ways of saying the same thing, or f dashed of x. So that is equal to negative 6x over x squared plus 1, all squared on the bottom line. Another way to think of doing this, and which is kind of the way I look to do it, is I kind of call it the cover-up rule, where you treat one chunk of the function as though it was an x. That is, multiply by the power and reduce the power by 1, then multiply by the derivative of the chunk, so that's the thing you've covered up, that you treated like an x. So I'll explain it with this example. So example 3, here we go, u equals 5 over x cubed minus 2. So what we can do is write it in index form, just so we get that term on the top line there. So we've got 5x cubed minus 2 all to the power of negative 1. Then what I do is I normally, in class, I'd use my whole hand is to cover up what's inside the brackets. But normally I'd just, even if you just use your finger, so you get your finger and you cover up what's inside the brackets. And then what you want to do is you just want to differentiate around what you've just covered up there. So when you do that, you're going negative 1 times 5, and then just copying down what you've covered up. So that's the x cubed minus 2 to the power of, and then taking 1 off that power, so it's negative 2. So have a look at that line, and hopefully you can see what's just happened there. Then I remove my finger, and then you just multiply by the derivative of the part you treated like an x, or in other words, that you covered up. So the derivative of x cubed minus 2 is just 3x squared. And then it's just a matter of simplifying. So 3x squared times 5 times negative 1, we've got a negative 15x squared times by x cubed minus 2 to the power of negative 2. And then, of course, what we know is we can just look to write that in the same form as the question. So putting that term on the bottom line, so we've got negative 15x squared over x cubed minus 2 all to the power of negative 2. So this is the way I end up solving them. I call it the cover-up rule. Like I said, I'd use my whole hand on the whiteboard in a classroom, or when I'm doing it is using my finger and just covering up what's inside the brackets. So give these a go. Page 266, exercise 15.02. If you can try every question, I think it's just good, for you to build up that stamina, because you definitely want to be strong on this before we move on to more advanced questions. All right, good luck.